It's the language of the universe.
But I don't understand it.
Welcome back, everybody, to the Math and Physics Podcast. I'm your host, Parker.
And I'm Ray, and we welcome you to episode number 42, where today we have a very special guest. We have Dr. Steinberg, our quantum mechanics professor from our second year of university. I think we've mentioned this class a lot, and this might sound a little cheesy, but I also think we have said very explicitly that this was one of the most interesting courses we've ever had at this university, just because of the concepts, the ideas that were taught to us, just so interesting, and I really appreciate it. So, Parker, what do you think?
Definitely, yeah. It was also one of my favorite courses, and, I understand that we only saw the concepts at a basic level, and so for Christmas, I actually asked to get a couple of books. I got QED. I don't know if you can see it. But it's QED by Richard Feynman.
Good choice.
And Quantum by Manjit Kumar. So I'm going to have a good read.
That's amazing.
The next semester into the summer before we start the follow-up course.
It's nice to hear such good feedback about the course, but especially that it motivated you to aim your Christmas presents in that direction. Glad to hear it, and I hope they work out.
Yeah,
definitely. So, go ahead.
Yeah, so Dr. Steinberg, maybe now we can come to a small introduction into, what kind of physicist you are. And I mean, obviously we know, but tell the audience. And, what kind of professor, what do you really, what all do you do at U of T? Because I'm not sure, because I know a lot of professors are, professors. They help graduate students, they help doctorate students, and they have a lot of roles. So maybe you want to introduce yourself in that manner.
Sure, I'm happy to. I am an experimental physicist, and I specialize in quantum physics, but particularly atomic, molecular, and optical physics. So I guess when I was hired, I would have described myself as a quantum optics person. That's one of the names for our AMO physics group, the Atomic, Molecular, and Optical Physics Group. But I developed more and more of an emphasis on things like quantum information and quantum foundations as time goes on. Mm-hmm. So basically, we use the tools of optical and atomic physics to study foundations of quantum mechanics, what quantum mechanics really teaches us about the world and how much of that we can demonstrate, but also how one manipulates information in quantum systems and what information can teach us about the quantum nature of the world, but also what quantum mechanics teaches us about the nature of information. Mm-hmm. And obviously, these are things that you hear about from time to time related to technologies like quantum communications, cryptography, and quantum computing. And a lot of what we do, we try to aim at understanding the sorts of things that will feed better into those fields. We don't work on building a quantum computer in my lab, but on things that relate to that and help us devise new sorts of error correction or data compression or quantum logic gates, or even the techniques for characterizing those quantum systems.
Wow.
Now, as you said, professors do lots of different things. Obviously, as the two of you know, I teach, or at least I attempt to. I hope that works out. And as you said, I supervise graduate students. The way you phrased it, I'd say, is usually more appropriate to something like a history professor or maybe a math professor than a physics professor, rather than saying that I help doctoral students. I would say that I rely on the doctoral students to do the research that we're doing, especially in experiment, right? I describe myself as an experimental physicist when I was a grad student and postdoc, and maybe for the first year of my professorship, I was working in the lab. And by now what I do is really supervise a bunch of experiments and help my students design and create and build and maintain these experiments and then analyze them. But in physics, it's very much, and especially in experimental physics, the graduate students who are really doing the day-to-day research. And if we talk more about the research later on, the work I'll be describing is stuff that I like to think I've guided and in some cases spearheaded, but that was really done by the remarkable group of students that we've got at U of T.
That's amazing.
Yeah, that's awesome. So can you tell us about the first time where you knew that physics is what you wanted to do, or the first maybe idea that sparked in your head that said, wow, this is absolutely amazing?
Yeah, I mean, it goes back far enough that it's almost something that I spent 10 years trying to escape just before I convinced myself that no, that really was it. It was my destiny. Um, my dad was an electrical engineer, so I sort of, grew up hearing about scientific kinds of stuff. And in retrospect, I can see back then that our different perspectives already meant I was not going to be an engineer, but something like a physicist. He would try to explain to me simple concepts of electric circuits. And, I like knowing how you could build something, but the way that a real engineer works, where, they want to know how can I buy a chip that does all these things, that never interested me because I wanted to know what was inside the chip and I wanted to know how the transistor worked and I wanted to know why the electrons did what they did. And one of my early memories about that was him just telling me that electrons were, I don't know, maybe he was telling me about orbitals and atoms or something like that, but he explained they couldn't be in the same place at the same time. And I asked him why, and he just got so impatient with me. That's just the rule. You just go with it. And I think that was when he gave up on me and pretty much lost interest. Even years later, he would visit our labs, and he would just love looking at all the equipment. And then he'd ask what in the world we're doing with the equipment, and he would just shake his head at what a waste of time it was to ask these abstract questions when we had such fancy equipment that we could just use to do something more practical. But honestly, when I began studying it, I probably, like a lot of physicists, you ask, the answer is a little bit embarrassing. It's that I was a Star Trek fan. I wanted to know what would you have to do to build a spaceship and build a Starfleet. And with a friend, we used to come up with plans for what this fleet would be like. And this I also remember well, that someone told me at some point that there was a real complication to how you land a spacecraft, and they went into some sorts of details, but I asked, probably at that point, my stepfather about it. And he said, oh, I can't answer these questions for you. For that, you need to learn calculus, which was a great way of getting rid of me. So I spent a summer reading a Calculus Made Easy book. And by the end of the book, I realized I still have no idea how you would have to land a spacecraft. And he said, oh, maybe it's not really calculus. Maybe it's physics. And I don't even think I knew what physics was at that point. But from that point on, I started trying to study physics when I could.
Wow.
What really kind of cemented my path, I think, was years later reading, again, some kind of science fiction book, actually a really weird book, that brought up ideas about Schrodinger's cat and entanglement and so forth. And crazy book, but it actually had a glossary that explained a lot of its concepts. And in the glossary, it even explained what Bell's theorem was. And talked about Alain Aspec's experiments, which years later I realized how remarkable it was, because this book must have been published a few years after Alain Aspect did his Bell inequality experiments, and these science fiction authors were already using it and explaining it.
Wow.
But the way they described entanglement and Bell's inequalities, they said something like once two particles have interacted, they remain forever connected no matter how far apart you take them. And these days I would take issues with the detail of that phrasing, but the idea that you could even think to prove such a thing and what it would take to prove it just mystified me. And from that moment on, and again, I was probably 13 or something at the time, I was just reading a book. I was just driven to take a quantum mechanics course as soon as I could to find out where do they get these wild ideas. And I've pretty much been stuck ever since.
So that was your goal from the beginning, was to go directly to quantum mechanics.
Yeah. I mean, I liked physics fine, the way you like solving puzzles or whatever. And I would solve the, blocks rolling down the inclined planes. And I liked the fact that I could get the right answer. But honestly, I couldn't care less about blocks rolling down inclined planes. I wanted to know about the atom. I wanted to know what the world is made of, like most people, I guess, who go on to study physics. I thought more in terms of particle physics at the time. And, I'd watch TV specials explaining about quarks and gluons. And I wanted to know what was next. And I wanted to know about black holes. But the thing that really stuck with me was not, which particles are made of which other particles. That's zoology or botany at some level. It's what are the rules that governs all of it. And as time went on, I learned that was really quantum mechanics.
And did you always want to become an experimentalist, or were you maybe kind of leaning into the theorist side and then you're like, hey, maybe this is not for me or something like that? Or was it always experimentalist?
I don't think I had a strong view of that early on. I mean, I don't know how much you guys know or think about that distinction at this stage, right? When I was a second year undergraduate, I probably didn't think about it very much. Um,
Mm-hmm.
and, I guess I was one of these people who was good at math by high school standards, but not necessarily by the standards of physics majors at a good university.
Mm-hmm.
I was fine at it, but I can't say I enjoyed just like struggling through integrals and so forth.
Mm-hmm.
And at some point I thought about it, and I guess I had this image of what it would be like to be a theorist. And, as much as I would love to solve the riddle of quantum gravity or what have you, I tried to picture what would you do day to day as a theorist, waiting for that inspiration. And maybe I just didn't have enough good role models, but I just didn't see what I would do staring at that blank blackboard, wondering what to do. Whereas I kind of understood what you would do day to day, between inspirations as an experimentalist, that you're really just trying to do something concrete while waiting for the next idea.
Mm-hmm.
But again, a lot of it has to do with role models and also with timing. And I think this is something you'll see no matter what. That there are many different paths you could follow, and who knows which one you will take. But the people you meet along the way and the people who mentor you are going to be a big part of that. And I'm sure I could have wound up doing other things. But the guy who was the director of undergraduate studies when I was an undergrad, so like, as a shy student who didn't really approach my professors much, the guy I had to go to once a term to get him to sign my schedule was really outgoing. And, honestly, like most physicists, if you asked him, what are you working on? You'd get a 2-hour response, no matter who you were. He was so excited about it. And he was a great teacher and a great researcher.
Mm-hmm.
And I ended up doing my senior thesis with him. And he taught me about a lot of what was going on in the late 80s in atomic, molecular, and optical physics. He told me about laser cooling and the fact that you could cool and trap individual atoms. He told me about the fact that the electromagnetic vacuum could have physical effects on these cold atoms. He taught me about time reversal symmetry and the fact that you could use spectroscopy on atoms to look for evidence of the fact that the universe is not time reversal symmetric or mirror reversal symmetric. And these are the kinds of deep issues that I wanted to keep studying. Mm-hmm. So I think it was largely his influence that made me think of that. Years later, when I started getting interested in quantum information, I realized if I'd been an undergraduate or a starting graduate student in those days, there's a good chance that would have grabbed me, that there are so many deep questions there and problems that were ripe for being tackled, almost like being in the early days of quantum mechanics, where, in 1928, if you had learned quantum mechanics, you just would say, here's a problem no one's been able to solve before. Let me try it with quantum mechanics. And if you were reasonably good at it, I think there was just a lot of so-called low-hanging fruit. Mm-hmm. And part of me feels that way about quantum information. And, maybe the early, somewhat easier stuff, all the pioneering work has already been done, but there's still so much out there. So starting out these days, I'd be more torn between theory and experiment than when I was making the choice. And, a lot of theorists were just either striving to go off and do string theory, where, 99 people out of 100 never even get a job. Or maybe just doing really, really detailed calculations that I didn't see the interest in. Mm-hmm. And I think that's evolved. But I think, it's not really what you asked, but to give a kind of bit of unwarranted advice, I'll say that people often think of the most exciting aspects of a career and the biggest questions you can ask and what happens on, the best day of your year. And that's not what life is about. Life is also about the day-to-day. So you want to be working on something where the big questions excite you, but you can do that in many different fields. You also want to work on something where you have what it takes to get through the hard times and where you're going to enjoy the struggles. True. And I think the point is there are some people who really enjoy fighting with recalcitrant equipment, even if the question doesn't matter to them. And there are people who really enjoy staying up until 6 a.m. doing some coding, even if, it's just to write a video game. And there are people who really enjoy solving an integral just because they get caught up in the abstract mathematical thought. And the question is, where are your talents and where does your patience lie also?
Yeah. Wow. That was pretty deep conversation for sure. Thank you for that advice. But one thing I definitely want to ask before we move forward, the picture on the back on your background, was that chosen for a reason? Because that maybe looks like an experimental team or something.
Yeah. That's part of my team lab taken
Okay.
under COVID, as you can see from the picture. So
Yeah, yeah.
we're basically not getting together in the lab these days. For quite a while, the lab was shut down entirely, and now we're basically allowing one person on an experiment with full social distancing rules. Behind you is our Bose condensate apparatus,
Oh, wow.
where
Okay.
we cool and Bose condense rubidium atoms. So get out of the way, you'll see it better.
Oh, wow. It's
And
pretty
over
intense.
there on, let's see, from left to right on my screen, it's probably right to left on yours. In the red mask, there's
Yeah.
Nick, and then Joseph in a bluish one, and then hidden off in the corner is David, who's now the senior student on that experiment. And we were having some vacuum problems and thought we needed to change the rubidium, and that's kind of a complicated, delicate operation. So that day, we all came in together, and I thought, while we were all there,
Why not?
masked up like the Lone Ranger, yeah, we needed a photo of the team.
So your entire team is comprised of these three people and you, of course? Or are there
No,
more
so
and this is just the
there,
experimental part or something?
no, our whole group is primarily experimental.
Okay.
Often some of us work on theory papers together. Only once that I can recall have we had a sort of pure theorist in the group. And that was a postdoc who's been helping to supervise some of these experiments. But there are about 10 graduate students at the moment, but they're split onto roughly 4 different projects. And the Bose condensation project currently has these 3 graduate students. And there's also an undergraduate who's been working with us, Grace, mostly on coding and some theoretical stuff. Normally, we get undergraduates involved in the physical research as well, but given these rules about distancing, that's just not practical right now. So unfortunately, we don't have any undergrads working in the lab. Honestly, even for the new graduate students, it's a concern what COVID means for these labs, because it's the kind of thing you need to learn from one another. There's no way to learn experimental physics except on the job.
True.
And you learn to babysit one apparatus that becomes, your child. And you have to pick up the ins and outs of that apparatus from the people who've already known it for years. So right now, for a while that wasn't going on. We just had, the senior person on each experiment who knew it best, able to come in and work on it. And now, little by little, Joseph, who's number 2 on this apparatus, has been taking it over, and that's good. But he doesn't know all the ins and outs yet. And there are things that I'm sure David could do more quickly. It's good because Joseph's got to learn them anyway. And he's just, taking his time to try to figure it out. And David's still around a bit longer to give us the tips when something really hits a stumbling block. But for instance,
Imagine if
for
Joseph
Nick,
and David
harder.
are listening to this podcast and are like, okay, these are tips for me now. I'm going to improve.
I'm not saying anything that they wouldn't agree with and already know. I'd be pretty circumspect about that.
And this lab is in the basement of McLennan, right?
That's right. So we've got 2 pretty big rooms in the basement of McLennan. And one of them has traditionally been our atoms lab and the other our photons lab. And in the atoms lab, we have 2 different laser cooling experiments. This is the more recent one, although I think that still means we started building it in 2001 or something like that. And in fact, although it keeps evolving and each grad student brings their new ideas and technical improvements to the thing, we're all kind of in consensus that it's about time to really refresh and rejuvenate this thing, move on to a next generation. It recently reached the biggest goal that I had set out for it when we started building it. But that goal itself is really only the first step towards a lot of pretty deep questions we'd like to address. And I think we're going to start butting against the limitations of that apparatus. So one of the big tasks for Joseph and or Nick and or whoever joins the group next is going to be either building a completely second apparatus or more likely kind of building some stuff in the background and then migrating the experiment little by little to a replacement apparatus. We're going to have to see how that goes.
By the way,
Awesome.
quick note, McLennan, for, I don't know, the audience members maybe. So McLennan Physical Laboratories was our building, our physics building for basically most of our classes. And episode 36, QED, the live episode that Parker and I did, The first scene was filmed in McLennan. So I think that's pretty, just a fact, just a quick fact.
Yeah,
there.
we just did a little introduction there.
Yeah.
But
And do you know who McLennan was?
no.
Oh, it was a person. Oh,
It's
I
named
didn't.
after a person.
Did not
And
know that.
I'm probably going to misspeak. So I don't know. You guys probably weren't at the department holiday party a while ago. They decided to have a trivia game. And I'm glad I didn't participate too actively because most of the trivia was things like what year was the Department of Physics founded and who founded it and so forth. But if I'm not mistaken, McLennan actually kind of founded our physics department. I believe he was the first physics PhD awarded at U of T. And confusingly, that was before the department existed. So he got his PhD and then went on to create the department.
Department.
But I guess, in the 100 years ago, that was how things were.
Wow.
Yeah.
That's amazing. So yeah, this next question is, pretty big, pretty general, but if you had to explain to the general audience, right, how quantum mechanics really reshaped our understanding of the universe, what would you say?
That's deep.
So, yeah, I mean, you guys know I'm hesitating because that's a big question for me, and I've been talking to both of you about it for most of the term. And there are different ways to look at it, but yeah, I would say that unlike most physical theories that just say, oh, things don't really behave the way you thought, they actually all fall at the same rate, or, stars are actually other suns, or things like that. To understand quantum mechanics, you end up having to change your view of what it means to picture the real world, what a description of reality would be. And not just, as people often say, descriptions of really small things or atoms or electrons, but of everything. There's just no way to make the quantum mechanical theory of atoms consistent with a kind of more classical, Aristotelian or Newtonian or whatever view of rocks and planets and you and me. And I really think that's different from, learning, hey, what do you know? Light is made of electric and magnetic fields. That really changed how we thought about light, but it didn't change how we thought about anything else. How I think about me and you or, water waves or anything. So to me, there's something more deeply philosophical about what we learn from quantum mechanics. And how to best put it? I guess, the most popularized aspects of it are not 100% accurate. One of them is randomness. And although, again, I've discussed with you guys the subtleties of that, we don't have any proof that the world is random. The most natural way to look at the theory of quantum mechanics does make it look like there's randomness fundamental to the laws of physics. And that's certainly a big change. And even if you don't take that interpretation and try to look at it differently, there's something in there that changes, that things I used to describe definitely, the moon is definitely there, the earth is definitely here. Quantum mechanics says you can't really describe things like that. If nothing else, particles are described by wave functions, which means that they have uncertainty. And I think from the modern viewpoint, especially driven by everything we've learned from quantum information, that would be one of the big things to say, that the information about the world is a different thing according to quantum mechanics than you would have thought according to our classical intuitions. And the most complete description that we think is possible of things in the world is still a description that leaves some uncertainty. And that's pretty striking. And that's the kind of thing I was alluding to before. How could you know such a thing? How could you ever know that your description is incomplete, right? It's one thing to say, I don't have all the information. It's another to say it's impossible to have all the information. And more people think that's what quantum mechanics teaches us. And again, that's not something that can be proved, but even if you sidestep it, it deeply changes the way you have to think about reality. So the way I always explain it is that classically, there's some way of describing the state of a system. You look at a pool table and you see where all the billiard balls are, and I just tell you where is each ball, how fast is it moving. That's a complete description of what's going on. And to me, what quantum mechanics has taught us is that the description of any system involves making a list of every possible kind of classical state it could have, and saying every one of those has a kind of weight to it, something like a probability. And to describe what the world is doing, I need to give you that whole list of weights for all the things that could be happening, tell you how likely they are to be happening. And again, as you know, on the technical side, how likely isn't sufficient. But to the layperson, I'd say that kind of gets the idea across. You don't say the cat's alive or dead. You say, how likely is it to be alive? How likely is it to be dead? And that's the right description of what the cat is doing.
Right.
So how satisfied are you personally? This is a very completely opinionated question. How satisfied are you with accepting this view of reality, that some things are just impossible to know? Like, are you like, because for it, like, the main reason I bring this up is because I was watching a video on Richard Feynman where he was, I forget what it's called, but it's one of like the Richard Feynman interviews, and he was basically kind of expressing how, you know, he enjoys the fact that there are some things that we simply cannot know, and he's okay with it. And there's nothing that,
Are you sure he said that? Or just some things that we don't know?
I promise on an interview, he was like, I like, okay, I can't quote him, but I can definitely link the video in the description below, but I can't bring it up right now because I forget which one it was.
That's fine. Please do
but
send
I think
me
basically,
the link later.
yeah. So my question is
I'd be
basically,
surprised
are
from
you
him
satisfied?
to say that. Certainly, you know, I'm not only am I satisfied with there being things we don't know, but that's what makes science fun. That's what makes science interesting. It is the quest for new things. And, you know, again, something you don't necessarily appreciate while you're taking courses, although by this stage, hopefully you do, and you certainly should, is that science is not about learning lists of facts and learning the rules that we already understand. It's learning how to progress beyond them, how to ask new questions and answer those. And I think it's a fascinating, you know, again, philosophical question of whether there are things we could never know or could never understand. You know, there are people out there who say there is an ultimate theory, but it's probably just beyond us. And I'm not sure what I think about that. Whether I think that the human ability to abstract things is so powerful that in principle nothing is beyond that ability, or whether that's hubristic and there really are clearly things that would always be outside of human capability. You know, obviously there are things that are just too much for any individual human to understand. But the great thing about that is by now there's almost no one who understands all of the workings of the laptop that I'm on right now. But it doesn't matter. People get the big picture. They chunk and, you know, they're emergent phenomena. As for this quantum idea, that maybe that's just how the world is, it no longer bothers me at all. Again, you know, I don't like jumping to conclusions. I wouldn't want someone to tell me we know that you can't have all the information because I don't think they've proved that. If they proved it to me, then I'd say, okay, that's fine. I'm no longer so disturbed by it. My tendency, and this might just be common to experimentalists who have this need for a real visualizable picture of what's out there, is rather to say that you could, in principle, have a complete description of the world. You could, in principle, imagine writing down the wave function for the universe. And when people say that's incomplete, it's because they have the wrong idea of what a description should look like. Right? They're trying to ask, where is every electron in the universe? And to me, that then just becomes a misuse of language. That we're used to this classical way of seeing the world, but that's not really what the universe is like. It would be like asking, is the universe a nice guy? It's just a stupid question. The universe isn't a guy. It's not described by the emotional adjectives that I apply to human beings. And similarly, when I ask where are all the electrons in the world, I'm using the language that I use to describe, you know, pebbles in front of me on the beach. And it's just the wrong concept, the wrong language. I think when I was a student, that was kind of a modern way of thinking, to really picture the wave function as a real thing that could be out there. And as I've gotten older, I think it's become less modern. And by now, I think the people who really pioneered a lot of these quantum information ideas and those who moved on to work in foundations that I have the most respect for, I think they see my viewpoint as old-fashioned. And they would say, no, actually, Bohr was closer to the truth, and the wave function is really only about information. It's only a description of what we can say about the universe, and it's not something that's really out there. But this is one of the debates that's so interesting, and it goes on now, and people write papers about what the consequences would be of interpreting the wave function as a real thing in the world, or interpreting it as just a description of information. More and more right now, it's trendy to try to understand quantum mechanics through this lens of information. Saying maybe I should back up, as I've told you guys, but not necessarily your audience.
Exactly.
One of the things that distinguishes quantum mechanics from a lot of other theories in physics, like the theory of relativity, is that it's not like Euclid's elements. It doesn't begin from some postulates and then derive things from that. Special relativity, you say, let's make these two assumptions and see where they lead us, and they lead to the entire theory. And quantum mechanics was just built up as this house of cards to support, what we saw experimentally. And in retrospect, you can go back and say, okay, I could build it from these 3 or 4 foundations and call them axioms. But the axioms weren't designed because of any philosophical ideas or even any experiment that showed us, that axiom has to be the case. And a lot of people feel like we'd understand the world better if we had the right set of axioms. If we said, oh, the reason quantum mechanics is true is because the universe wants to be like A, B, and C.
Mm-hmm.
And we don't know what the right, elegant set of axioms is. So many people now have this intuition, and it's nothing more than an intuition, that information theory, the power of quantum mechanics for treating information, might be a better way to do that. There have been a lot of interesting speculations about how you could write information theoretic axioms that would get you a lot of the underpinnings of quantum mechanics. But it's still a work in progress, and as I say, it might not lead anywhere. It's just how people like looking at the theory.
Mm-hmm. Wow. Yeah. So I think now we have come to the point where this question had to be asked, and we also talked about it before the interview. The episode. Quantum computing. So quantum computing, I think, is the most searched up quantum topic maybe on Google for a long time, because I think especially right now,
Well, you can't trust Google. They've invested so much in it that, of course,
that is also true. That is also true. Maybe that's not the best source, but what I'm trying to say is it's a very popular topic with a lot of people. So I think I don't know too much about quantum computing, I will not lie, but I believe that they have to exist in very cold temperatures, correct? Like, am I right with that? Because I'm pretty sure I saw that somewhere. Like near
Not
absolute zero,
necessarily.
correct?
I think it depends on the architecture. Most of
Okay.
them do involve low temperatures.
Yeah,
It's certainly true that, what we mean by low temperature is getting rid of, random motion
exactly.
noise.
Exactly.
So most physical systems that you want to control accurately need to be at some kind of low temperature. But whether that's low compared to room temperature or low
Mm-hmm.
compared to the surface of the sun or low compared to liquid helium depends on the details of the system. So honestly, although one way or another, yes, you need to make the system well controlled, what that means in terms of a practical temperature depends on what you build the computer out of. Even a lot of the best classical computers used to have to operate at cryogenic temperatures.
Wow, I didn't know that.
So the
Okay.
reality is we don't know how to build a quantum computer right now. We have a lot of different ideas
Mm-hmm.
for things that could in principle build quantum computers.
Mm-hmm.
And we've made a lot of progress on several of those architectures, and there are a lot of companies as well as university and government researchers out there around the world doing this. Which one will be the best, either in the short term or in the longer term, we don't know. And the answers to those two questions might be different, right? We used to build computers out of vacuum tubes, and that was great. And once we learned how to do it out of transistors, that was even better. And we learned how to do it out of other kinds of transistors that we now incorporate in chips. That's even better. And similarly, I think it's very, very likely that we'll build some small scale but still useful quantum computers over the next 10 to 20 years that, let's say, maybe rely on ion traps. And maybe in 50 years, no one will be using ion traps anymore. They will have found some way to do it with Majoranas or with electrons floating on helium or something that's just much more scalable that no one's even thought of yet.
Mm-hmm.
For a while, it's likely that these technologies will coexist, and some may have different strengths and weaknesses. That again is also true classically, even though our classical digital computers now all use basically the same ideas. There are different paradigms, right? There's serial and there's parallel computing, if nothing else. But for a long time, there was analog computing. And some
Mm-hmm.
applications, there still is analog computing. And I'd say similarly with quantum information, there are ideas that are kind of closest to digital computing, just a quantum analog of classical digital computing that are mostly what people talk about. But those might be the hardest to achieve. And there are other approaches that kind of look a little more like doing a simulation or an analog that I think are going to be very, very powerful for certain applications. So at least for a while, it's likely that we'll have both. Maybe that's even true in the long term.
Do you ever see, or I mean, I don't even think this is maybe important because who would ever use this, but do you ever see a quantum laptop? Like a laptop that, runs on qubits,
No,
like a quantum processor.
um,
Yeah.
I
Or
personally
or
don't.
is that just a stupid idea? Like, what do you think?
It's not a stupid idea. No, and
Okay.
it's a worthwhile question, and people ask these questions. You've probably seen these quotes from I forget who it was, the CEO of IBM, might have even been Watson. I don't know who said he foresees a market for 5 or 6 computers in the United States one day. So it's dangerous to be too pessimistic about these things. The thing with quantum computers is that they're not fundamentally a new way of building computers that just speeds up the process that you guys already understand when you think about computing. It's really a different approach to dealing with information.
Mm-hmm.
And we've determined that there are some particular little applications where we know that would be at least a little bit faster than any possible classical approach. I don't mean faster in real time because they're physically different devices, so one might have a higher clock speed than the other, but that the number of steps required would scale better on the quantum device. And then there are a lot of applications where it's not provable because we don't really know the limits on classical computing. But if you trust the expectations most computer scientists have, there'd be a huge advantage, an exponential advantage to the quantum device as you get to larger and larger problems. So one of the things a lot of people are trying to do is to figure out what's the range of problems for which that would be useful. And there are a handful of problems where we know that it seems to be useful. And many, many problems that people work on day to day where I just don't see why it would make a difference to do it quantum mechanically. So my expectation is that there's always going to be a trade-off, that to make a system well controllable quantum mechanically may involve cooling or other things, but that's going to have some extra cost, whether it's a financial cost, an energy cost, a space cost, or just a trade-off in the clock rate. It's going to mean that unless there's a reason to do it, you wouldn't want to bother. So what I could picture is that one day our laptops will all have quantum coprocessors, so that when you need to call an algorithm that quantum mechanics is known to be better for, like every time you need to, break someone's credit card, it's good to use quantum mechanics for that, then it'll call the quantum processor and do that. The same way that we used to have floating point coprocessors, and now we have graphics processors and so on and so forth, and even processors that are kind of optimized for doing certain deep learning tasks and that sort of thing.
Mm-hmm. So it's not I don't know how to put this. It's not like a replacement for what we have now, but just a supplement, so to speak.
That's the way I see it. I don't see any good reason to replace most things we do now, as long as you're just doing kind of sequential operations. You're doing word processing, or even if you're doing graphics or something like that. I don't immediately see the reason. Now, I could believe there's stuff you would do in the background quantum mechanically that could even speed up graphics. But one of the tricks is that what a quantum computer does is it makes use of this insane richness of the amount of information in a quantum state to have more paths that it can take to go from the input to the output. If you think of the job of a computer as marching along from input to output, the funny thing is that there's no difference in the size of the input or the size of the output that you get classically or quantum mechanically. So even though people like to say, quantum systems can be in many states at the same time, so the quantum computer is solving many different problems in parallel, the fact is there's this bottleneck at the output. It can't give you any more information at the end of the day than the classical computer would have. So if you have, you want to program some 3D graphics on your 20 megapixel display, it's not as though you can use 30 quantum bits and say, 30 quantum bits, that stores 100 million complex numbers. It doesn't matter. At the end of the day, you have 30 bits coming out. You can't fill up your display with it. And if you want to fill up the display, you still need your 20 million bits. The question is, do you want to do some processing along the way where you're willing to throw out the intermediate steps and you still have that same amount of output at the end, but the acrobatics you needed to go through to get it just took up more space than you had in the classical system? That's kind of where the quantum thing can be useful. So for most tasks, I just don't see it. But one of the big questions now is whether for things like optimization, serious quantum capabilities offer an advantage. And there are a lot of different ways I could mean that question, and there are a lot of different perspectives on the answer. But yeah, it does make it seem to me like most likely it will supplement abilities. And whether it supplements them in a way that's going to be useful on your laptop or mine, I don't know yet, but it's conceivable. The idea that it could provide abilities that are important in certain niche applications, like doing quantum chemistry, which is important for drug discovery and materials research, or basic physics research for that matter, that currently seems very, very likely. And a lot of companies are banking on the idea that different kinds of quantum computers might just help with miscellaneous optimization problems. And again, that's possible, but I think the evidence is still less strong, except in a few cases. Like, there are a few famous problems you may have heard of. There's the traveling salesman problem. People who read a little bit about computer science like to hear this one. If I give you a list of cities, I show you where they are on a map, and I say your job is to deliver packages to all of them as quickly as possible. Draw the fastest route that connects every one of these cities. It turns out the time it would take to solve that problem grows exponentially with the number of cities. So our fastest computers cannot find the exact solution for 20 cities. And there are real companies out there spending real money on this because, FedEx and UPS, that's what they do. Well, it's not what they do, right? They use hubs and so forth. But, they do try to solve that kind of optimization problem. Many other problems can be cast into the same form. And again, as far as we know, it's exponentially difficult on a classical computer. But no one's been able to prove that. Tomorrow, someone could turn around and come up with an algorithm that breaks that belief. But that would stun most of the computer science and math worlds. The thing is, almost no one expects that a quantum computer would be able to solve this problem either. What we do is we come up with approximate solutions. And it turns out that classical computers are already very good at coming up with approximate solutions for that problem. And there are companies like D-Wave that think that their quantum computers
I was going to mention them, yeah,
are even better. And, well, they're a company, so they periodically just say, we know it's better. But if you talk to an academic, you'll realize that's not true. And for a while, a lot of academics were really very dismissive of D-Wave and thought they were being kind of misleading and said that, no, it can't do any of this. But in fact, the people who went to study it more closely had a much more balanced and nuanced view at the end and did find certain things where they said, here it really does seem to be behaving differently from a classical machine. And I can't yet prove to you that it's using that to good advantage, but it is doing something classical, and there are certain classes of problems where it seems like it might be faster. So there are related approaches where, as I said earlier, the jury is still out. Was the other optimization problem I was thinking about? No, I lost it. I had another example in mind, but I've forgotten what it was.
Yeah. Do you think that quantum computing with, maybe 20 years down the line could be the key to reaching the technological singularity? Because that is kind of impending doom on the human race, and it's just a matter of time before we get there.
Well, whether it's doom or paradise, I don't know, and I certainly don't share your certainty about that singularity. I think it's a really amusing idea, but no, I tend to find it an unlikely hypothesis for various reasons. But even if I took your view that we are heading towards that singularity, I wouldn't expect any particular role for quantum computing there. If I wanted to make the case, I could. It's always true. I could say part of what slows us down from the singularity is designing new materials, knowing how to manipulate the world, manipulate matter. that requires quantum mechanical simulations. And one of the things we really know seems to be exponentially difficult on classical devices, but could be done on a quantum computer. And in fact, the idea that led Feynman to sort of propose the idea of quantum computers is to simulate other quantum systems. So you could imagine that these artificial intelligences that are out there trying to design new technologies and create them faster and faster would need that materials aspect of it. But I think that's a far-fetched view of things.
Parker, are you up?
Yep.
Okay, so I think we can just continue talking. So now I think that quantum computing definitely got some sense into your ideas and your opinion on it, and I think that was a very interesting opinion, because I kind of thought that maybe, like similar to Parker, that quantum computing might have some role for this quote unquote singularity, but maybe not. Who knows? So one question that I had was, I was reading some of your publications, and I was reading this one where you were measuring particles tunneling through a barrier, and you were measuring the time spent by atoms in certain excited states in this barrier, right? So I think there's a pretty, I don't know if this is a valid question, but how would you measure such an interval of time? Because I guess if you have that apparatus like in your background, I guess you can maybe see, the particle states or something. I'm not sure, maybe have some observation, but how would you measure the time interval that goes along with that? That's kind of my question.
It's a harder question than maybe I mean, the experiment we did was to measure this tunneling time, which we happen to do with rubidium atoms, which has been a topic of debate for 90 years or something like that. And I would say a big part of the reason it led to such long debate is that the question of how much time does something take is actually a really tough question to define. Even classically, I would say time has a very strange character classically. I forget who it was, maybe even Augustine or someone like that, who said, if you ask me what time is, I don't know. If you don't ask me, I know. And it turns out that depending on exactly what you mean by measuring a time, you can get different answers. And some people interpreted that to mean the question is meaningless. I don't tend to go that way. I would instead say we just need to learn how to be more careful about these questions. There are different things that we can mean by the concept of time. Let's learn to be careful about which is which and how you'd ask each of them. But I'll say in passing that the nature of time has remained one of the deepest questions in physics. Forget about how long this particular process takes. Why are there 3 spatial dimensions, at least, and only 1 time dimension? Why do we all move in one direction in time? Why can we ask where something is in space, but not ask where it is in time? Right? Everything has one position at a given time, but it doesn't necessarily only have one time at a given position. These are deep questions. Why is there an arrow of time at all? In our particular experiment, we took what I guess I would like to describe as an Einsteinian viewpoint, that when you ask questions, you need to think about what it means in practice to ask that question. To ask how far apart are 2 objects, you've got to think, what does it mean to measure how far apart they are? Otherwise, it has no meaning if it's just angels on the head of a pin. So time is what a clock measures. And for our experiment, we wanted to know how long atoms spent in a given region. So we decided the individual atoms should carry their own stopwatches, and we'd set it up so the stopwatch only ticked when the particle was in the region of interest. And as I said, that's one way of defining what we mean. I think that's a well-defined question, but there are others you could ask. Mm-hmm. And, how does a clock work? A clock generally relies on some cyclical evolution, right? The Earth going around the sun, or the Earth rotating on its axis, right? Those were the original clocks. And from that, we learned how to make pendula and things like that. And then, needles that turn around on dials. And there are a lot of different quantum mechanical proposals for how you would define a clock quantum mechanically. Some of them invented to help people build experiments like ours, and others just to address the question, what is the nature of time quantum mechanically? People just wondering what would happen if I defined a quantum mechanical clock. In our case, we took basically the simplest thing that can spin. We took something that looks like a needle that can point in different directions in space, and that's the angular momentum vector of a particle or the spin vector of a particle. If you put a charged particle with angular momentum in a magnetic field, it precesses the same way that a gyroscope precesses under the influence of gravity. And we know that rate of precession, so we can use that as a clock. In our case, we used a funny pair of states of the atom, but it's kind of an analog to this magnetic picture. In fact, they're the same states that people would use to build an atomic clock. Atomic clocks are made generally out of alkali atoms. The official definition of the second is for cesium, which is down below rubidium on the periodic table, but we make them out of rubidium as well. And in fact, about a decade ago, some of my colleagues in AMO physics, I think principally Kurt Gibble at Penn, realized or demonstrated that rubidium would have been a much better choice for defining the second than cesium.
Wow.
But because of properties of rubidium that no one knew about when they defined it, it was too late. In any case, we use those two states as a kind of clock. And as you surmised, what happens is after the atoms go through the apparatus and get through the tunnel barrier, we can measure the state of the particle. Now, quantum mechanics being what it is, you make a measurement and the state collapses. There are a number of different outcomes you could get. You get one or the other. So in fact, you need to do it over and over again, maybe millions of times, in order to get the statistics. And what you find is that you can't measure the angle of the spin, but you can do one measurement where the probability of seeing the atom goes as cos squared theta, and another measurement where it goes as sine squared theta. And if you do this measurement over and over again, you can estimate what cos squared and sine squared theta were and figure out what theta must be. And that's kind of how we measure the time.
Wow.
What's more important from my point of view is that since the particles carry their own clocks, we can separate out different groups of particles. And to me, that was what we were getting at here. That was, I think, a little bit deep and addressing what I see as a problem in the way people think about quantum mechanics. People always tell you what you're not allowed to ask in quantum mechanics, what you're not allowed to measure. I can't know which way the particle went. I can't know how long it spent here. I can't know which slit it went through or whether the cat is alive or dead. And what we've been trying to show in a lot of our experiments is that view is overly rigid and simplistic. And at least on an approximate or a probabilistic level, there are things that we can learn about a particle and about its past. So we can fire a particle towards a barrier where most of them are reflected, but some are transmitted, and ask, how long did just the transmitted particles spend in the barrier? And that's a question that, in the textbooks I grew up on would have sounded illegal. That would have been exactly what we were told. Bohr taught us you can't ask these questions. And what we're trying to show in more and more of our work is you can ask those questions. The answers may not be, black and white, hard, fast, but you can get approximate answers. And there really is a different amount of information I have available about a particle that was transmitted versus a particle that was reflected.
Okay.
Awesome.
Wow.
Well, I had like a couple of questions I wanted to ask you, but it looks like we're coming up on close to an hour now.
I have been over talking, as is my habit.
No,
That's
it's awesome.
fantastic. That's fantastic. That's why you're here, right? To explain quantum mechanics.
Yeah, well, it's a what's the term? Professional malady. You make someone a professor and suddenly their job is telling people things all the time. Then it becomes difficult to shut them up.
Yeah.
Occupational hazard, I think.
So yeah, I mean, we'd love to have you on for another episode where you can ask all the questions we wanted to ask you. But yeah, I think we can end this episode here.
Yeah.
Unless Ray had one more thing.
No, I mean, I mainly just, I really wanted to understand that time, because I was like, okay, to be honest, because what I thought, I don't know, this might be really stupid, but because I put this in my question, but I said, do you maybe have like a super slow-mo camera and like you see the number of frames that it takes for the rubidium atom maybe to cross, and then you see the time? I thought maybe you did something like that. Clearly, that's not quantum mechanical
enough. Question also. No. And there are things like that you could do.
Oh,
The
you
question
can?
is, would you expect to see the same thing? And the
Oh,
answer is no. I
okay.
think you'd expect to see something very different if you were really taking the pictures. So we're really trying to ask, what was the atom doing when I wasn't looking at it? Because I know that if I looked at
True,
it, that would disturb it.
because picture means photon is hitting it. That is true. That is true. Oh yeah, I guess picture's the wrong way then. Okay. Yeah, well that's basically it. So
Okay, perfect. Well, thank you so much for coming on to
absolutely.
our
Well, thanks
podcast
for
today.
having me. Like I said, I think it's a great initiative what you guys are doing.
Thank you.
And I wish you great holidays and great luck in your next semester.
Thank you so
Yeah,
much.
have a great holiday. And are you teaching next semester as well?
I am, as a matter of fact. I'll be
Same
teaching.
same class?
No, that's as far as I know, at least not offered in the spring, only in the fall and in the summer.
Oh.
I'll be teaching a class called something like Math and Science in Current Society or Current Topics in Physics. I've actually forgotten the names. It's a
What year?
JPH course. It's listed as a fourth year course,
Oh, it's a
so
fourth year
one
course.
can
Okay.
certainly take it in third year as well. It actually is currently designed to fulfill the ethics requirement for physics specialist students.
Uh,
So it's kind of more a course about how science is done and how it should be done and what some of the pitfalls are and how it's related to society and what happens in the real world rather than a straight science course.
that's
That
right.
But
sounds
maybe I'll see you guys in
fascinating.
it one of these years.
Yeah.
Yeah. All right. Well, for our audience, if you enjoyed this episode, make sure to follow us on Spotify or go watch on YouTube where this video is being recorded and posted. You can ask us any questions in the comments or follow us on Instagram at math.physics.podcast, or you can send us an email by taking that and adding at gmail.com. We will be posting clips as well, we started last week. We
Yep.
started posting clips on YouTube and Instagram and soon on TikTok.
TikTok, exactly.
Yeah.
I was just gonna say.
So, yeah, thank you so much for listening. And this has been episode number 42 of the Math and Physics podcast. I'm your host, Parker.
And I'm Ray, and we will see you soon.
Bye, guys.